There we go. Hello. Glad as always to see that some number of you were able to join me for the live stream. So nice to see you here. If you're watching the video later, hopefully you're having a good week. We're in week 9, which means we're now over the halfway point. So a college semester can be a grind, I know. So you guys have good energy in your classes, and hopefully we keep that up. The problems become more challenging over time because you are developing a skill set, and to continue to build and grow your skills, we need to give you more interesting problems to work on. So it is true that the problems will get slightly more challenging over time as we expand the tools that we have to solve those problems. But it also means that the problems are a lot more interesting to work on. And I hope you find, like I often find, that when you tackle a challenging problem and you solve it, that it is, it's a very satisfying feeling. It's good to overcome challenges. So at least I think it is. So hopefully you have a positive experience as we hit this second half of the semester. We have a project due on Sunday this week, and I did a starter on it. And if you're watching, then you're already in the habit of watching, so you know that. If you know people who don't watch, then you could help them out by telling them, hey, we actually have been looking at least partial solutions to some of the problems in the project, the second project that's due this week. And then I'm looking forward to I'm kind of talking ahead of us, but I'm looking forward to the third project, because that's the first one where you get to, if you are so inclined, you can be creative in a variety of different ways. You can be technically creative. You have some space to be kind of artistically creative if you want to. So we need to get through the second project and feel strong about that. But good stuff coming, at least in my opinion. Okay, so the discussions were really good. So whatever it was that you guys did to kind of just knock the ball out of the ballpark last week during discussion, I look forward to reading more of those, because you guys did really good research, you did really good posts. There were lots of good examples. I hope as you're reading your classmates' posts and you're seeing these comparisons between the Go language and other programming languages, that, hey, like everybody does many of these things in mostly the same way, which means that moving between different programming languages is not an intimidating prospect at all, at least for the basics, right? It's the problems that we're solving which tend to get more challenging, but the languages needn't to be a barrier to us. Once we have one language like Go, with a fair amount of experience in it, then we can move between languages relatively easily. So I do have a note on my agenda about reading the labs. So I will stop and do that today, but the vast majority of you're just kind of, the labs are no problem, and you motor right through them and you do perfectly. But I know it can be frustrating to lose points on the lab, and you realize that you lost points because you simply didn't read the assignment carefully. So I'm going to stop and focus on the rubric, and remind you that I wrote the assignment, of course, but before I start grading each week, I go reread the assignment to make note of what it is that I asked you to do, and then I grade accordingly. So I'm going to encourage you to redouble your efforts to read the lab requirements, the rubrics, carefully before you call a lab complete. And you should also do the same thing for projects. So we'll look at that one closely today as well. Let's first let's look at this week's content and see what we are looking at. So last week we looked at decision making, which is if-else statements and switches in Go, and hopefully the lab gave you some sense of what the decision making is about. It allows us to reach different solutions or go different directions based on the conditions of our running program at any given time. We can do this thing, else we can do this thing, else we can do this thing, by sort of creating conditions that lead to different outcomes. So repetition is what we're doing this week, and the whole point of repetition is that there are some problems that are best solved repetitively. Your second project, as an example, has a number guessing game in it, which is not a complex problem to understand at a high level, but in terms of code, it has a repetition component in that you should allow the player to keep guessing the numbers until they guess it right, or if you want to limit the number of guesses that they have, then you might create conditions where you allow them to repeat the whole process of guess the number. And then it also has in it a decision element, because each time they make a guess, we have to compare it against the random number generated by the computer and let the player know if they're too high, too low, or if they have found, guessed the correct number, which I think of as a Goldilocks problem, if you want to think about it that way. So decision trees are very good for Goldilocks problems, too much, too little, just right. And then looping is good in that case because we want to let the player keep playing the guessing game. We also need a loop on the project, the ability to perform a repetition, because our program should continue running. It should have some sequence of events that repeats itself over and over and over again until our player says that they don't want to play any games anymore. So that's two places in our project where we need repetition. I just used the term loop, by the way, which is what we call repetition constructs in programming, as we call them loops. Things that kind of cycle back around on themselves for some amount of time or based on some condition. All right, let's walk through the module. So I should have added one. I'm going to add one here. Well, no, you'll see it. We're actually, yeah, I'm going to add it, and then I'll add it to the other class as well. So single condition, counting for loops. We also want, why won't it do anything? It's very strange. There it goes. And I'll fix the other class as well. So we're going to look at 3 different ways to set up loops this week. There are additional ways we can set up loops in the Go language, but we're going to focus on 3 of them this week, which sounds like a lot, but they're all based on the same building blocks, and we will explore what the differences are between them. We will, in our lab this week, look at situations that have been created that require that we create loops to solve them. So we'll look at problems and algorithms, the solutions to those problems that loops are well built for. And we'll do all that in the context of functions. So we will continue to practice using functions to implement our code in nicely designed chunks. And we will continue to use unit testing to ensure that our implementations are correct. Okay, so readings are not extensive, but hopefully, and these of course are where the questions are asked from, but hopefully you've also found some supplemental materials that you're comfortable with, that can give you additional ways of looking at and describing these techniques that we're learning in class. Homework as always. Lab I will come back to, I think. Yeah, let's come back to the lab. Let's see. Oh, yeah. So similar kind of discussion this week. And again, this is to expose you to the way programming languages work. So you'll learn this week and experiment with how we do looping, repetitions in the Go language, and then go do some research on how other language do repetitions. Turns out that there's more variety in the way different languages do repetitions than there is in the way they do decision making. Even though fundamentally they're all designed to do the same thing, which is allow us to set up a situation where we can do something repetitively to get at our solution. The classic, by the way, looping algorithm, that's actually a bad looping algorithm. Maybe we'll practice on it today. I don't know if they still do it, but pick up a shampoo bottle at some point and read the directions. And the classic directions on a shampoo bottle are lather, rinse, repeat, which is a loop. Lather, rinse, repeat. Lather, rinse, repeat. That's a looping construct. It is a broken looping construct, by the way, because there's nothing that tells you when to stop. Who knows when you're supposed to stop? So on a shampoo bottle, they assume that you know that you should stop when your hair feels clean, but a computer won't know to stop unless we tell it to by coding a stop. And then reminders, and the big one is that the second individual project is due this week. I'm going to very quickly, because I've had exchanges with a couple of people this week saying that they had lost track of where the projects are. So the projects are always in the reminders page of the module. Whatever the next project is always mentioned and linked in the module itself. So if you are looking at the entire module, then you will see the links to the projects every week. I also typically mention them every week during the live stream and then in the lecture video. So that's another place, if you have heard of people who, like, how are you keeping track of the projects? Well, he mentions it every week, and it's in the reminders page every week, and it is on the course home page always and forever, linked there with its due date. And you should probably also have this kind of to-do list in yours, which tells you what's coming up sooner than later. So Canvas itself has a whole bunch of places, and my course has a whole bunch of places where the projects are linked and reminders are there. But you, of course, also have access to a variety of technologies to help build and maintain a to-do list for yourself. So that's 99% of you. This is not a problem as far as I know, but there's a small contingent of people who say that they've had trouble tracking the project. So there's a reminder about, I've tried to put them kind of everywhere all over the place, but the course homepage has the entire semester laid out. So that's always a good place to go. All right, let me go back into the module, go to the lab, and then go over and talk about new stuff. Okay, so let's look at loops. So I'm going to do some bad programming on purpose here a few times tonight. So I will tell you, like, what I'm about to do is bad and wrong, and it will cause a problem. So if you're following along, if you hear me say that, you might wait a moment and kind of see what happens when I do what I do, and then see how I solve the problem that I'm going to create. So loops are they're really the first thing that we have used in the Go language, where we can make something that runs wrong and badly. Now, we have had opportunities to make mistakes in our arithmetic and have mistakes in our outputs and make compiler errors, but loops can really go awry. And I'm going to show you just right off the bat how loops can go awry. So don't do this until after you've seen me do it and then solve the problem and tell you how I solved the problem. So this is CSCI 20 week 9. Week 9 is very good news. Okay, so bad thing coming up. And I will label it. In fact, let's put it in all caps to make it really pop. So our main worry when we are using loops is that we create what we call infinite loops. An infinite loop is something that repeats itself infinitely because there is no way to stop it. And I'm about to write one. And then I'll show you how to deal with it should you get yourself in this situation. So infinite loops are bad. We don't want them. They can happen because we can make mistakes in our logic or in our design. So if you do one, it's not the end of the world. You need to know how to deal with it. But it is something to be mindful of, that I don't want to create infinite loops, but I'm about to create one. This is the Go language looping construct 4. What it means is that the Go language is going to execute the contents of this block here, and it's going to go back to the top of the block and go back down through the contents, and then go back to the top of the block, go back down through the contents over and over and over again until something causes it to stop. Oh, let's put it. Okay, so this is a bad loop. It is a poorly designed loop. So what it will do, though, is when the program comes to this section, it will execute the contents of the for loop block. So it'll print 1, print 2, print 3, print go, and then it will return to the top of the block and repeat it. Print 1, print 2, print 3, print go. And it will do that until something causes it to stop doing that. This is an infinite loop because there is nothing in the code that will stop this. So I'm going to run it, and I hope that Replit doesn't get mad at me, but here we go. So this is an infinite loop. It is doing it forever and infinitely because nothing in the code has it not do this. If this happens to you, you hold down the control key. Well, you click in the console part. Hold down the control key and press C. So control C, and you'll see at the bottom of my screen, hopefully it says signal interrupt. Do you see that? You do. Signal interrupt. So that's, and then this little caret C is where I held down the control key and hit C. So what I'm telling you is that infinite loops are bad. If you have one, stop it with control C. You don't want these, but if you have one, you do control C and it will stop. Oh, that's true, Kevin K. Yeah. So in our Linux class, we get a lot of practice at doing these kinds of things on the command line. That's very true. So now our Go programming group. So if this never happens to you, then that's great. But just so you know, if you create an infinite loop, click down in the console part, hold down control, press C, control C, and that will stop your infinite loop. It needs to be fixed, but it will stop it. Let's go again. Control C. So anyway, let me show you another bad version of this. This is the worst kind of infinite loop. Is an infinite loop where you can't see anything happening. So watch what happens if the loop doesn't actually perform any code, execute any instructions. Oh, let me get rid of fumped. All right, here we go. Seems to be stuck. And the answer is it is. It's repeating nothing forever. So if the program looks like it's stuck when it shouldn't be stuck, there's a good chance that you have a for loop that is caught that isn't doing anything that you can see. So how do we kill it? We do control C. So that's an even worse kind of for loop, is that you can't actually see anything. It just looks like the program hung up somewhere. It's a possibility that there's an infinite loop in there. So be on the lookout for that kind of thing. Okay. So how do we, so if this loop is kind of by design an infinite loop. How do we fix it? Well, let's comment that out, and I'm going to use the same loop, but I'm going to fix it. Get rid of these things. That does not look right. Okay. You'll notice the same rules apply, by the way. So when I'm in a block, everything in it is tabbed over at least once. So how do I then, if this is what I'm referring to as the forever style of loop. It's a legitimate loop if you know how to manage it properly. So this is a bad, unmanaged infinite loop, but we can manage it. And the way we do that is, well, one way we can do it is we can ask the user if they want to see this happen again. So let's print a message down here. I'm going to do 2 line breaks after the go. So let's print a message, and we will say go again. Yes or no. And then we will read that in. Okay, so the way that you always cause a loop to stop when you want it to stop is with some kind of condition. Every loop that we look at today is going to have a condition somewhere that we use to control when the loop stops. So I'm going to use a user input. I'm going to use a user input here to establish the condition when I should stop. And the way I'm going to do that is I'm going to use an if statement that will stop this when the user says they do not want to go again. So if they answer no here, yeah, then we want to stop, right? So this is a forever loop, and we have this go again. So if their answer that's stored in that variable go again is no, then we break. So you'll see in the agenda it says break statements, and what a break statement does is it breaks the nearest loop. In fact, I should add that. Did this leave room? It mostly did, didn't it? More styles to come. Let's do this, and then we still have room. Okay, so a break statement will break a loop in the Go language. And what I mean by break a loop is that immediately this loop stops executing, and the program will continue running after the end of the for loop. So let's put a statement here. Telling ourselves when we got to the end. I'm going to put a line break in front of it too. Okay. So here's my setup. I have this for loop. Oh, by the way, I forgot to tell you this. You can check your curly braces to see if they're matched by clicking on them. So notice that when I click next to the curly brace on the if, it highlights its opening partner. That's a good thing. If I click on the curly brace of the for loop, it highlights its opening partner. If I click on this curly brace, I may have to scroll up, and then I will find, oh, there's its opening partner. You can go from the other direction as well. You can say, where does the for loop end, by clicking next to, on either side of it, the opening curly brace, and Replit will highlight its partner for you. Okay, which is a way to keep track of the matching pairs, because every opening curly brace has to have a close. All right, I will also point out to you quickly my styling, my formatting. So everything in the for loop starts one tab over, but then when I get to this if statement inside of the for loop, I have another block opening up, so I tab everything inside of it one over as well. This may seem like there's no value in this to you at this point in your career, but once you get used to reading code, if it's formatted properly like this, it is so much easier to find what goes with what in code if you have it formatted like this. And it's what everybody in the world will expect you to do. And if you don't do this, no one will want to code with you. And coding is a lot nicer when you have partners to work with. So if nothing else, you want to have nice styling so that other people will want to partner with you and work with you. Okay, so how am I going to stop this for loop? I am going to let the user decide when to stop it. So I ask the user a question, I read in their answer, and then I condition breaking the loop on that answer. I should, by the way, say if it's a little n or if it's a big N, then we break out of the loop. Break statements break loops. They don't break decisions. They have nothing to do with the decision. They have everything to do with what's the nearest loop. So this break statement breaks whatever the nearest loop is, which is this loop. Which means that instead of going back to the top and repeating 1, 2, 3, go, it will break to the next line after the loop at that point. All right, so here we go. Oh, now I have commented out fumped and get a compiler error. All right, let's run it. All right, so there's 1, 2, 3, go again. So it's waiting for me to type an answer. I'm going to say yes. It repeats it again because an answer to yes didn't cause the break, which means that the loop cycled back to the top and came back down through itself again. So there's 1, 2, 3, go again. Now it asks, do I want to go again? Yes, I do. So it goes back to the top. So now let's type a no. And what should happen is that that piece of logic will trigger and break the loop. And breaking the loop, which it did, means that the program pops out of the loop and continues from whatever follows the loop just below it, which in this case was, this is the end. Okay, so that is a forever loop. I don't use these very much, to be honest. I am not, it's just this, sort of the whole idea of purposely having a forever loop. I don't use these a ton. I use other setups, but the key is, does your forever loop have some moment where it breaks? If it does, well, that's okay. Then that's fine. All right, let's look at a different kind of loop. That's the forever loop. All right, so now let's look at a condition loop, and what I'll call a single condition loop. What do I want to loop for? Oh, I don't know. Let's do one. We'll do one on an integer. Should I do one on a random number? Nah, I don't need to do that. So let's make a number. So the thing to note here is that the first thing I do when I'm about to set up a condition loop, as opposed to a forever loop style, this is a condition loop. What did I call it in the notes? I called it, yeah, the condition style. That's on line 16 here. So this is a condition loop. And what I do before I build my loop is I create a variable, in this case called number, and I'm going to use that variable to define the condition for this loop. In fact, let's give the... No, let's not. So here's how you do that. You still use a for loop, but here, after the word for, you establish your condition. It's kind of like an if statement in that it is a true-false condition, But the difference is that for a for loop, true means allow a repetition, and false means pop out and go to the end. So let's put a statement here. That we have exited the loop. I'll put an extra line break in front of it. Okay, so this is where a condition goes. So let's define one. Let's say while number is greater than 0, the number is and then we will run it and see what happens. So now I have a loop based on a condition. If the condition is true, then the loop will execute. So chat question coming up here if I have anybody who is brave enough to answer one, but let's try it before I ask the question. All right, here we go. We have exited the loop. It never said the number is anything, so what happened? And I'll just give it a moment or two. So don't feel pressured. I can answer it, but I thought I'd give you a chance if you're out there and you want to. Okay, so what? Okay, so BB Latte is venturing an answer that the number has never been stated. So that's a good thing to think about. So the number has been declared. So number exists as a variable, but for some reason, this is not true. Number greater than 0. That's also, Shamar is venturing a good thought. Do we need an if else here? We don't. So the whole problem is that the loop is conditioned on number greater than 0 being true. So why does the loop then never execute? If the loop is conditioned on number greater than 0 being true, why is number greater than 0 false, in other words? That's correct, Shamar, so it's not true. So number is declared. So you have to remember in Go, if you declare an integer and don't establish any value, what value is it? It is 0. So it's important to remember in Go that variables are zeroed automatically unless you override that behavior with your own value. So since number is 0, and that's not greater than 0, the loop never actually executes even once, which is something important to know. Some condition loops are designed so that, well, if the condition isn't met, I'm not even going to do anything even one time. So that can be the case that some loops will never even execute through their bodies once because the condition isn't meant to start. So let's make the condition true. So we'll set it equal to 1, and then we will fire off the loop. Infinite loop, infinite loop, infinite loop. Let's Control C. I'm trying to Control C. There we go. Oh, I didn't click in the console. Click in the console, Control C. Okay, so I got stuck in here. And the reason I got stuck in here is because if you have a condition loop that's conditioned on some variable, somewhere in the loop, that variable needs to change. If this variable number, which controls the loop, is never changing in the loop, then we have a problem. So one thing that we can do is we can simply count the number backwards each pass through the loop. So we will print out the number, and then we will decrease it by 1. And then the number, so hopefully everyone's following this. We print out the value of the number, we decrease it by 1, then we return to the top of the loop, and the condition is checked. So every time the loop is completed, it goes back to the top and rechecks the condition to see if it should do it again. So let's see what happens. The number is 1 and then nothing. So Kevin, let's see. Can we do, I think it does. Can we combine that up into number minus equals 1? Yeah, okay, we can. So I'm going to put it back, Kevin K, but yes, you are more than welcome to use that that setup. I tend to do this kind of more drawn out versions of things for the PNA 1 class, so that we get in the habit of kind of really studying the code. Yeah, that is interesting, isn't it, Shamar? So we can restate this whole setup as number minus equals 1, which they mean the same thing. So yeah, I'll go ahead and leave that breadcrumb if anyone wants to use it. Okay, so hopefully everyone's seen the condition here, and the condition this time is based on the value of the number, which starts at 1. So initially 1 is greater than 0, so we see the number is 1. Then 1 is subtracted from the number, which it becomes 0. The loop gets to its end, it goes back to the top, and now it rechecks the condition. And what is number now? It's 0. That's not greater than 0, so we are out of the loop, and we continue with whatever follows the loop. So if I bump this number up to 10, let's say, let's go 5. If I bump that up to 5, then we will see it goes 5 decreased by 1, checks the condition, 4 decreased by 1, checks the condition, 3, 2, 1, and then 1 becomes 0, and that breaks the condition, which breaks the loop. So notice I didn't have to use a break statement here. It just stopped. Yeah, okay. So let's add one other thing. Let's go up this time. So let's start at 0 and go up to and including 10. Correct. So Shamar asks, so when this condition is not true any longer, in other words, when it's false, then the loop just stops right there, and the answer is yes. When this condition becomes false, the loop, the program will just jump immediately down to the next line after the loop. As long as this is true, the loop repeats itself over and over and over again. When this becomes false, the program will jump to the next line after the loop and pick up where it, and continue with whatever follows. So you can have things before the loop, you can have things after the loop, and of course then you have the things that go on in the loop. Okay, so let's switch the logic around a little bit. Let's count up this time. Oh, it can go into negatives. So the Dan bar asks, can we make it go into negatives? So yes, we can. So we could say as long as we're greater than negative 10, let's say, then we can go down. Because integers can be negative. So now we go 0, -1. And notice, by the way, negative 9 becomes negative 10. But negative 10 is no longer greater than negative 10. It is negative 10, so it stops. We can go all the way through and including negative 10 if we want to. So yeah, we can count backwards, and we can go into negatives if we want to. Or we can count up. So now number plus equals 1 would be the same. We can count up. We can also, by the way, so I have a note there, break statements. We actually can do break statements here as well. So we can, if we want to, we'll just see that behavior. We can add additional logic in here, and we can break just on things. So let's just say, for example, if the number is 7, break. I think of this as short circuiting. So we have a loop that's designed to go all the way up to and including 10, one at a time. But let's just say for some reason we don't like 7. So when we reach 7, we're just done. So you'll notice we get to 7, we get to 6. The number counts up to 7, and then when we check for 7 and break the loop. So this is unusual to do this. But you can use break statements in condition loops as well. It would be more typical to do something like this. Let's steal this code. It would be more typical to do something like, I'll have to clean this mess up a little bit. That comes back. So it'd be more typical to sort of combine a condition loop, which is what I have here now. It'll go up to 10 if left alone, but also maybe the user might want to choose themselves to stop at some point. So we can use breaks in condition loops is the point. So we're at 0. Do you want to go again? Yes, I do. We're at 1. Do I want to go again? Yes, I do. 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 And I'm just going to say, yeah, as far as you want to go, loop, keep going. Now, I said I want to go again in that case, but now the loop condition stops the loop. I chose not to with my short-circuiting break option, but the loop was designed to only go up to and including 10 anyway. But it also means that I can say, well, yeah, but now I'm tired, so no, I'm not going to do that anymore. So you can combine condition loops with break statements if that makes sense. We will rarely break a condition loop like this. It does happen in our class. It's unlikely that we're ever going to need this, but it can happen. Some of you, I'll say not normally. You may decide that you have found a solution, and that it could be true, where this makes sense for you to do it. Okay, so it's a condition loop. Can it have a break statement in it as well? Yes, it can. But it is less common that we would do that. Normally we would, if we write a condition loop, we're going to use the condition to control the repetitions in the loop. Okay, let's do another one just so you can kind of see how this goes. So let's say we have 2 integers. Let's make this be 10, and we'll make this be -5. And we'll just kind of have x and y go past each other until they reach 0. But we're going to create a loop that has a condition that if either our x or our y reach 0, then we're going to stop. So here's what that's going to look like. We're going to say for x is not equal to 0. So as long as x is not 0, we want to keep repeating. And also, we don't want y to be 0. So now we're going to set up a condition that is combining, checking 2 different conditions in combination. So as long as it's true that x is not 0, and as long as it's true that y is not 0, we'll repeat. So what we'll do is we will say format f x equals something, y equals something, y, and then we will go down with x one at a time. We will go up with y one at a time, and the loop will stop when either of them reaches 0 on its way up and down. Okay, so there's x being 10, y negative 5, and now you can see x coming down, 9, y is negative 4, it's going up. X is 8, y is 3, they're coming toward each other. Here's x, well, depends on how you see it in the camera. X is going down, y is going up. So x is 7 now, y is negative 2, x is 6, y is negative 1. X would be 5 next, but y reaches 0, and that is one of the conditions that breaks the entire loop. So we can also do combinations of our logic and condition a loop on multiple variables. So this is saying if x is not 0 and if y is not 0, then we are good to repeat the loop. We can also do this kind of thing for we can do this on user input as an example. So let's say we have a string. String, and we will just, let's just leave it empty. So this is an empty string, and let's condition a loop on this string. So let's say while, so as long as the input is not equal to stop, then we'll do stuff. So this is an empty string, meaning it's nothing, and nothing is not equal to stop, so that's okay. So we'll print it. And let's surround it by quotes, shall we? So these weird things that I've set up here, that backslash is called the escape character in this context. So if we want a quote to print, we have to precede it with a backslash. So the only thing that'll show on the screen here is the quote, and then the string in between, and then another quote. The reason why we have to do this weird backslash thing is because the quotes already do something in Go, which is mark the beginning and the end of a string. So if we want the quote to actually be inside of what's the output, we need to precede it with this, is what we call the escape character. So current input is that thing. And then we will ask the user, let's do it again. We'll put, no, because they might, any word or stop to stop, I guess. Sounds funny, doesn't it? Okay, so here is a condition loop. It's conditioned on the value of a string. Initially, the string is going to be empty, and empty, it is true that nothing is not the same as stop. So as long as this is true, then we will go through the loop once. So going through the loop once means that we will print out the current input, and then we will prompt the user to type something new, or the word stop, and then we scan that in, and then we go back up and we check the condition to see if they've typed in the word stop. So let's try it out. Stop to stop. What about stop? Nope. Oh, wait. There's a new line missing somewhere. I'm going to Control-C this. And I'm going to put a new line character in so that it doesn't look cruddy. So there's my current input is nothing, and that's because a 0 string is a empty string. So that's why the first input is the nothing that it is when I declared it. And now it's going to ask me, so if I do all caps stop, that doesn't match the condition of the loop and it won't stop. And I can say apples, and it'll print out apples, oranges. And now finally I will say stop, which ends the loop. And since there's nothing else after the loop, that's simply the end of the program. Okay, so those are condition loops. The conditions can be um, based on strings, integers, bools, true false variables, floats. You can write conditions for any kind of data, just like you would write an if statement, but you have to understand that for a for loop, it means, do I repeat true or false? Okay, let's do the third kind of loop so that I don't burn up all my time crazily. All right, so this third kind of loop is the most difficult kind of loop to write. But it's worth learning because you'll find that you use it a lot in specific types of situations. So we're going to go to the third kind of loop, which is a counting loop. And it's confusing because the entire setup for the loop controls is kind of built into the loop itself. So here's what I mean by that. But most of us will end up using this kind of loop frequently once we get comfortable with it, because we consider it to be a sort of a succinct way of describing the situation. But it can be confusing at first, so we will practice these a lot. This is a counting loop. I've actually used, my controlling variable is count. So what's going on in here? This loop is no different from this loop, and then I will get rid of this one. So these two loops, I'm gonna put a separator between them, are functionally exactly the same. This counting loop is no different in its behavior from this condition loop. It's just a matter of a different setup. So if in doubt, and if kind of intimidated by the complex looking setup, you can use a condition loop and it will work exactly the same way. The reason why we like these is in part because a lot of languages have loops that look like this, so you get used to seeing it and you get used to using it. The C language has it, the C++ language has it, Java has it. I can't remember if Python has it. Go, of course, has it. The Rust language has it. Many languages have it. This is Go language. This is a class for a community college in Northern California. So you're welcome to stay. But I have enrolled students in here. I'm teaching a class. For the college that I work at. Okay, so sorry, there's someone in chat that some of you can see that who's not an enrolled student, and I don't object, but just answering a question to them about what we're doing here. Okay, so these are functionally the same, but you'll find that a lot of languages do counting loops like this, so you get used to seeing them, you get used to using them, and after a while they don't bother you anymore, even though they're really weird. Okay, so let's break down the counting loop so we can understand how it's going to work. So this first piece is the same as this first piece. So count equals 1 happens before the loop actually executes the first time. And it only happens the once. So it's the same thing as declaring a variable. And in fact, I could have written it like this down here if I wanted to. This is the same thing. It happens before anything else happens in the loop's execution. That's the first piece. I call it the setup. Yes, so Shamar, you're right. Count equals 1 starts the counter at 1. Sorry, don't mean to be rude, but I can't have interlopers. interrupting me like that. I don't know what that person's up to. Okay, so one way to look at what we're doing here is this first piece is the setup. It's setting up a counter that will be the controlling variable for the loop. The second piece is the condition. The condition, just like in the for loop below, is checked at the beginning of every attempt to repeat the loop. So the loop will repeat so long as the condition is met, so long as it is true. And then we have the, I call it the adjustment. We have the thing that changes the counter so that eventually the loop breaks, right? So same down here, we have the setup, we have the condition, and then we have an adjustment that allows eventually the condition to become false, which is what we want. If the condition ever becomes false, we end up with a infinite loop. Okay, so they are intimidating. It's weird looking. The syntax is just kind of unusual, and the order of things takes a while to get used to. But we'll get lots of practice, so just be patient with it. It is odd. In this case, though, so we call them counting loops because we often use this arrangement when we intend to perform a repetition a specific number of times. So many of you will probably notice that this is going to perform this repetition 10 times. It's going to start at 1. It's going to count up 1 each time. So it'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, and including 10, and then stop. But let's prove it. So there it counts from 1 to 10, and then the program stops because nothing follows the for loop. So let's see what happens if we make it be 10 to start, just so we understand that the setup comes first before anything happens. The condition is always checked, even the first time through, and then the count is always adjusted at the end of every repetition. So it's weird. So we start at 10, which is less than or equal to 10. So we get through once, the adjustment happens, which means we're now at 11 and we break. Now, if we start this at 11, then note it never executes because the setup breaks the condition right from the start. And that can happen, and that's okay. Yeah, good one, Kevin K. So sorry, I got ahead of you a little bit in chat. The 10 did exactly as Kevin K said in chat, which is it printed out 10 and then the loop ended. And then I put 11 here just to draw your attention to the fact that a counting loop can still fail, or maybe by design not even get through a single repetition because the setup breaks the condition right from the start, which is okay. I mean, it's a little unusual, but it can happen, especially if you have the counter based on some external variable. So we might say, let's start the count at whatever x is instead, right, which would break it. Or we might say that the x is 5. So we start the count at 5 and then go up to and including 10. So this is a counting loop. That's what I call them, and I think that's what some of your readings call them. So we have 3 loops that we've looked at. We have the sort of forever style loop that needs a break statement somewhere in it to break it. We have the condition loop that has a logic condition that determines when the loop stops, which can also have a break in it. And then we have a counting loop, which is typically used when you want to do something a certain count number of times. Start here, go there, and repeat things that many times. They can also, by the way, have a break statement, but that is not something we'd normally do. I'm going to bring that comment up here. So oops. We will not normally break a counting loop with a break statement, but we can. Right, so it got to 7 and then it broke out. So the reason why that break statement thing shows for all 3 loops is because if you put a break statement in any kind of loop, it will break that loop. In fact, you can just put a break statement in. It doesn't make any sense to do that. But you can put a break statement in, which will break the loop immediately once it is reached. But we won't normally do that for counting loops, and we won't normally do that for condition loops. We will always do that for forever style loops because they will go forever unless we do that. So that's the 3 kind of loops that we have. Now we will add at least one more kind of loop in the not too distant future. All right, let me check my agenda and see where we are at. Yeah, okay, so let's look for some applications in this week's lab and also in the project. And start to be mindful of the time. Okay, so let me set up a REPL for the lab. I'll probably leave this one public. Okay, so let us go get the lab code and see what we can make of that. So I need the lab code itself. I need the test file itself. If you are having any struggles with the test files or anything, don't forget that there are instructions linked to every step of every lab to help you with the details. So if you are struggling with step 5, which is how do I create the test file, there are actually instructions there. And eventually the pictures will show with pictures that show you how to do that. So don't forget that there's instructions linked throughout these labs to remind you of the details of each step if you need that. So main_test.go, which is what it always is. So main_test.go, I think everyone realizes that by now, but if you struggled with it, it has to be called that. Exactly. This is one of those things in computer science, is that so much of what we do has specific rules about it that can't be changed, and that's because the computer doesn't do what we want it to do unless we establish and follow strict rules. The computer is completely a mathematical device, and it cannot do anything that is not tied to the specific rules of the mathematic and logic circuitry that it has. So the reason why there's so many of these, why does it have to have that underscore there? Because if it doesn't, it won't work. There's a lot of that, I realize, but it's just part of the nature of the work that we do. So anyway, let me get the test file and put it in my REPL. Paste that in, get the lab starter code. Paste that into my REPL. Okay. Let's run the test first. So let's just run the test. I should have done it verbose. So fails everything. Not surprising, but I'll do the verbose form, and I think I'm failing all of them. I am. Okay, so let's go look at the lab and see where loops can help us solve problems. So there's a get evens and a get odds. I'm going to do the get odds one. I think they are very, very similar. So let's see what happens here with get odds. So returns a string, okay? We've done something like this before just last week where we built the string by attaching new stuff to it. It's going to be something like that. returns a string containing the odd numbers from start, which is the first parameter. So from some starting integer to and including some ending integer. And then it will be a list separated by commas. So for example, if the start point is 1 and the end point is 5, then we should get 1 comma 3 comma 5 and no comma on the end. All right, so let's work on this. Hopefully you have the sense that because we are doing loops as the new thing, every function wants a loop. So basically what we need, though, is we need to go through repetitively the list of numbers 1, 2, 3, 4, 5, or from start to end, start plus equals 1 until we reach end. From start to end, we need to repeat the process of going from the start point to the end point, identifying which are the odd numbers, and then connecting up the odd numbers to a string. So let's set up for it. I'm going to get my output, which I will return, and then I need to build it. So we have options here. This is a good place for a counting loop. I don't have to use a counting loop, but it's a great place for a counting loop. But let's try it both ways. Let's try it. Yeah, let's try it all 3 ways. Why not? And then I'll leave them commented out and you can explore them when you're working through the lab. So let's start with a forever loop. I'm not the most comfortable doing it this way just because it seems a little bit weird, but it's fine. If we're going to use a forever loop, though, the very first thing that we should do, we're going to need a counter, though. Very first thing we should do is establish our break condition. So this is a forever loop, but we got to break it somehow. So we're going to have something that leads to this break. The question is, what is that something? Well, it should be when the counter reaches the end, then we will break. In fact, the counter should start at the start, shouldn't it? Let me separate these out a little bit. Okay, so we're going to get a counter. We will start it where we're supposed to start. Don't get confused by these examples. We don't know what the start point is. Could be 0, could be 1, could be 1,000, could be -40. We don't know. We just have to work with the variable. So wherever the person wants to start is where we start our counter. And then we are going to repeat a process until we reach a point where our counter is butted up against the end point, which is the second part. We don't know that it's 5. We don't know that it's 1. We don't know that it's 0. We don't know what it is. The start could be -1,000 and the end could be +1,000. We have no idea. So we have to develop an algorithm that uses the start and end points, not knowing what those are. Okay, so now we have our condition that would break the loop once the counter reaches the end. All right, so how do we use this counter? Well, we need to check it to see if it is an odd number. And the way you do that is that you take the counter and you mod it by 2. Var isn't equal to something. Let me think about that question for a second, Shamar, because I'm not sure if I answer, if I understand the question. But I assume the question is about, we don't know what the start in the, we aren't defining the start, no. The start is defined by the person who calls the function. So the start point and the end point are parameters to the function, which come from somewhere else. So you are correct, though, in saying that as the authors of this function, we don't know what the specific start point will ever be, and we don't know what the specific end point will be. All we know is that we will have to start somewhere and end somewhere and find all the odd numbers in between. Okay, so yeah, it's a good question. Hopefully I answered it. Okay, so we set up a counter starting at wherever the requested start point was. Someone calls this function from somewhere and gives us a start point. And then we break when we have a counter that reaches the end point. So what do we do with this counter? Well, the counter, in the example where the start point is 1 and the end point is 5, the counter will start at 1, and we want to check to see if the counter is odd. The way you do that is you mod things by 2, and odd numbers have a remainder of 1. That's the logic to find odd numbers. An odd number is any number divided by 2 that has a remainder, right? So 3 mod 2 is remainder 1. 5 mod 2 is remainder 1. 99 mod 2 is remainder 1. All the odd numbers will test out like that. So if this thing that's counting from the start point to the end point is an odd number, we are going to add it to our output. We can also do this, by the way. Oh, wait, can we? Is it going to be happy with that? It's not. We're going to have to do a format string. Yeah, so we're going to have to do this. So this is a little awkward, but we need, hopefully you remember that we did this sprintf trick in 2 to 3 weeks ago now. This little trick that I'm doing here, though, is taking a number and turning it into a string so that I can connect it to another string. So there's a lot going on there. I'll show you the error, though. So let's just say we try to add the number to the string. All right, so line 37, invalid operation, output plus equals counter, mismatch types, string and int. So you can't take a string and connect an integer. You just can't in the Go language. So if I want a string and I need to connect an integer, then I'm going to do this little trick. I'm just going to change it into one. So handily enough, the funct library lets me stringify an integer this way, and then it should run. Yep. And it's caught in a loop. I know this because nothing's happening and the program doesn't end. Control-C time. So something about one or more of these functions in main is caught in the loop. Aha. So this is a hard one. So I'll remind you about how loops, those last 2 loops we looked at, we had a setup, we had a condition, and then we had one other thing, and it's the other thing that I am not doing. So what's the other thing that I am not doing? Close. Kind of. So there were 3 steps in my other REPL. I had the setup, I had the condition, and then I had one other step that I needed to perform to make sure the condition could eventually be broken. So there's something about this setup and this condition that is presently the adjustment step. Good one, the Dan bar. I'm not doing any adjustment. So if counter is my setup and counter is my condition, then counter needs to be my adjustment. So it's the adjustment. So we won't have any print at the end this time. This function is supposed to create an output with a whole bunch of numbers and commas in it. So let's just run it against the test now and see what happens. caught in a loop, it would appear. I controlled C, get evens. All right, so get odds is still broken. Do I need to run this program to get it to compile itself? Counter plus equals 1 should have been okay. I'm going to click run. Okay. So apparently I need to click run before I do a test. So 13 comes out. I don't know what the heck that's about. Or do I know what that's about? Let's see. We are working on get odds. So get odds 1 to 5 printed 13, or in other words, 1, 3. So one thing I can immediately recognize is that the commas are missing. So I'm going to put a comma at the end of each number here as I'm building out the list of numbers. And then I'm going to click run. All right, 1, 3, comma. So I'm getting closer. So what's the problem now? So this is a hard one because it's a logic problem. So for some reason, I'm not reaching 5. And I don't know if you guys are going to be able to see it because it's a hard one. Something is wrong with my break. I'm breaking too soon. I'm breaking before I have reached the end point, which is supposed to be 5 in this example. So for some reason, I'm breaking before I get to the end point. And this is a hard piece of logic to work out. So that's correct. So when counter becomes, there you go. So Kevin K is on it, and Shamar is correct that we need this to be true a little bit longer than it is. So if we kind of walk our way through this, let's just go into the loop. We have an example down below where the start point is 1. Okay, so what happens if the start point is 1 and the end point is 5? Well, the counter will start at 1. That'll be odd, and it will spit out a comma. It'll spit out 1 and a comma. The counter becomes 2, and then it checks to see is the counter 2 equal to the end point in our example, which is 5? No. So we can repeat. So now, is the counter 2 odd? No. So this won't happen. Now the counter becomes 3. Is 3 equal to our example endpoint of 5? No. So now we check 3. It is odd, so we get 3 comma. We see that. Now it becomes 4, which is not our example endpoint 5. So 4 comes back through. It is not. It's even, so that doesn't happen. It becomes 5, and now 5 is equal to the end point, and the loop breaks. But the documentation tells us including the end. And Kevin K in chat has the answer. We need to wait until we have gone above the end point. Pardon me. So our problem with our logic here is that when we were stopping at the end, we weren't allowing a repetition for the end. We were stopping one short. So let's only stop once we've gotten the counter past the end, which will allow us to check the end. Okay, so we're close. 1, 3, 5 for our sample inputs of 1 and 5. Now the problem is we shouldn't have that comma on the end. So the comma is a problem for us. We can't just stick the comma on the end. So we should only be sticking the comma on the end in certain conditions, which is the last part of this algorithm. What condition would have us attach a comma? Which is a tricky one. But we're seeing that we're getting a comma after the 5 in our output, but we don't want a comma after the 5 in our output. We only want a comma everywhere before we get to the end. So what is the relationship between the counter and the endpoint where we do want a comma? What value is a counter? Is it okay to put a comma, in other words? Less than. Good one, Kevin K. So when the counter is less than the end, we want a comma. When the counter is equal to or greater than the end, we either want no comma or we want to be done. Uh-oh. Oh, I need to click run. What? Why are there 2 commas? It almost as if it didn't see that. Something ain't right here. Why are we getting 2 commas? Yes. Good catch, Kevin K. Wow, that's a tough one. So, yeah, we're getting commas for all of the counters, 1, 2, 3, 4, but we shouldn't have counters. And we shouldn't have commas for the non-odd numbers. So we need to move this if statement inside of this other if statement. Good catch, Kevin K. That was a tough one, man. So only for odd numbers should commas come out. Good catch. I didn't see that myself at first. Outstanding. So the condition of the comma is dependent on the condition of the odd number. And now we're in business. Good catch. Let's try a test on that, dude, and see if we get odds. Oh, brother. Look at this one. So when the start point was a 1 and the end point was a 1, that's the test on line 65. We put a 1 comma in there. That don't make any sense. The test on line 65. Let's check it. 1 to 2. Ooh, that's a nasty one. So we have a little bit more work to do on the logic because 1 to 2 is less than the end. So here's what we might try. So let's see, if 1 to 2. So when the counter is 1, that is less than the end. Well, equal to would still get it in there. So one thing we might try is to back up by 1 from the end and see if that helps. And if it doesn't help, then we'll try a different piece of logic. So let's back off the end by 1 and see if that helps, which is sometimes a way to sort of fix these problems is just step back 1 further and see if that helps your situation. It did help our situation to back up by 1. So we noticed that in the case where we start at 1 and end at 2, that we were getting 1 followed by a comma. But the 2, we're gonna get this stray comma, so we needed to back that one off by 1, and that seemed to fix the test. So let's call that a win. Pretty weird, huh? this problem is more challenging than you might think, which is the main reason why I wanted to implement it in front of you. So you could see a thought process go into it and see where all the logic is coming from. Someone asked, I think by Canvas inbox last week, by the way, can you, or no, it was in discussion. Several people pointed out that other languages allow you to nest things. And Go does as well. So you'll notice here that we have this for loop. Nested inside of it is this if statement and this if statement. And in fact, nested inside of this if statement is yet another if statement. And then a funky little piece of logic to handle the weird situation where the start point is one off from the end point. This is not the only solution to this problem, by the way. And this is awkward because we used the forever style of loop. So let's use a counting loop and see what difference that might make. So let's do the same logic, but let's use a counting loop instead and just see if that helps any. I'm cheating and I'm going to reuse some code so I don't have to type the stuff. But let's just see if the loop looks any better. And I'm checking my curly braces, to see that they all match. So there's the for loop, and I better check to see if the function still has its close, which it does. So that's good. That's it. So if I use a counting loop, you can see that all of the setup, condition, and adjustment is handled kind of in with the loop itself. And then the loop body can focus its energies on only the problem of the even, odd, and comma part. So let's run that. We still get 1, 3, 5. If we test it, let's hope that we still pass. We still pass the get odds. So I'll leave those there and share this with you for your consideration. Get evens is the same algorithm, except for instead of odds, you're checking evens. So hopefully that is a help to you. FizzBuzz. Okay, so FizzBuzz is a classic computer science problem. I'm going to do some setup on it. I'm going to run over. I'm sorry about that. Not a lot, but a little bit to help you with the FizzBuzz problem. So the FizzBuzz problem is a classic. There's kind of an urban legend about it. So if you go Google FizzBuzz, you'll find lots of discussion on this particular problem. The urban legend is that people get asked this at their first interview and they never know how to solve it. And I don't know if any of that's true. I don't know anybody who's ever been asked the FizzBuzz problem themselves, and I haven't. But anyway, it's a classic problem, so it's good to know a solution to it, yeah, even if you never get asked in an interview. So it's a looping problem, which is why it's here. So let's set up for an output, which we will return once we have built it. Okay, so we're given a max, and we're told that we are going to go from 1 up to and including max. So I like counting loops for this, so I'm only going to show you the counting loop solution. So I'm going to start a counter at 1. Why? Because this says go from 1 up to and including max. So my setup is going to be counter is 1. My condition is going to be counter as long as counter remains less than or equal to the parameter max. What that max is, I don't know. I'll have to discover that on the fly. And then the adjustment will be a plus equals 1 again, which is pretty common for counting loops. We want to examine every value between 1 up to and including max. Okay. I don't remember the algorithm. I'm going to have to go look at it. Okay, so here's the algorithm right here. So if I is evenly divisible by 3 and by 5, we print fizz buzz. Okay, let's try that. So if I, oh, what do they mean by I, by the way? This I that they're referencing will be our counter. So this I reference, I guess we could change ours to be an I, which is the classic way we name counters. And then that matches that leak code site. So instead of the word counter, let's just use a variable named I. The reason why we use this, by the way, programmers, we mean the letter I stands for iterations, which is a counter for the number of times a thing is being repeated. So you'll see people write their counting loops with I a lot. So that might help us when we read this. So if I, which is now our control variable, is evenly divisible by 3, which is how you do that, and it is evenly divisible by 5, not 2. That's how you write that logic. So this tests to see if we're evenly divisible by 3, meaning mod 3 yields no remainder. Mod 5 yields no remainder. Then we know that I is evenly divisible by both 3 and 5. We are supposed to say fizzbuzz. Okay, that's the first condition. Fizz if divisible by 3, buzz if divisible by 5. So understanding how decision trees is also helpful that you understand first match wins. So the second part will be if it is evenly divisible by 3 only. If it were evenly divisible by 3 and 5, this first branch would have already hit. So not a concern for us. I'm going to leave you a note here. That's evenly divisible by 3. Evenly divisible by 5. So this will not be working code anymore when I'm done. But hopefully it does help you solve the lab. And then finally, everything else. Everything else means it wasn't evenly divisible by 3 and 5 at the same time. And then we also check to see, was it evenly divisible by 3 only? Is it evenly divisible by 5 only? And then everything else is just the number itself. And we know how to do that now. Equals this funky thing to turn that counter into an I. And then the last step is those dang commas, but we already know how to do that from the other algorithm. So if that I is less than the max, and I always try that first and then decide if I need an adjustment -1 later. If I is less than the max, then let's go ahead and add a comma. Separate decision trees, by the way. So this is a loop that has 2 decision trees. The first decision tree is what is the main part of the output. Is it fizz buzz? Is it fizz alone? Is it buzz alone? Or is it simply the number stringified? And then we have to decide, is it okay to put a comma here? And then that's the whole loop. So I will share links to both of these REPLs in the lecture page this week. So you'll have access to the lab as I have. In the state I have left it, which is in a not working state because of this mess right here. but I didn't want to do all of it for you and take all your fun away. Okay, so there's the lab, and sorry again about running over a bit, but let's go open my project REPL and see if there is something new that we can do. And I know that you're going to need a little bit of help, so I'm going to indulge myself in giving you a little bit more help. Okay, so now we have loops. And now we have the ability to make a program that runs itself basically forever until the user says that they don't want to play anymore. So in the case of my setup for project 2, I'm going to wrap a loop around all of this menu stuff. And I'm going to check my alignments. So here's the for loop block that I've just added. Here is everything inside of it being tabbed over once. Here is a decision tree, and the contents of each block of the decision tree are also tabbed over once. So now I have a program that will run forever. Let's go ahead and set the break condition, but the break condition has already kind of been handled for us because that's when they press 0. And this decision tree already handles that. So number guesser, rock, paper, scissors, aha, come back soon. Game over. This break, remember, is for the nearest loop, and the nearest loop is the program loop. So this program will now run forever and ever and ever and ever until I say I don't want to play anymore. So number guesser, it just prints rock, paper, scissors, and then if I type 0, it should cause the loop to bust out. Come back soon. The program is over, so that works. This code I'm not sharing directly, so I'm going to leave this here for a sec for you to examine it. This is the main part of my setup for project 2, and it is not yet complete because I am not getting myself to the number guesser. Thanks, Shamar. Sorry you got to go. I know y'all, but I'll leave the videos up, of course, later. And sorry I'm running over, but I know we have this project, so I want to get you as much building blocks as possible. Okay, so now we have a program in the main part that uses a loop to continue the menuing sequence and the playing the individual games sequence forever until the user says I don't want to anymore, and then we break. Okay, so fortunately the rock, paper, scissors game doesn't need our help, but I am going to add something here because one of the requirements of the project, if I am not forgetting, is that we keep count of the wins and the losses. Yep, wins and losses. Okay, so we got to keep count of wins and losses, which means that we need to set up, so don't do this in the loop, do it above the loop. So before we get into the loop, we're going to set up number guesser wins, number guesser losses, which are integers. We'll also set up rock, paper, rock, scissors, paper wins, rock, scissors, paper losses, rock, scissors, paper draws. They're all integers. So let me show you how to do this part, and then we will stop when we get some part of the number guesser going. So maybe I can finish in about 5 minutes, I hope. Sorry about this. But hopefully you can use it to do the project. So we're supposed to keep track of win, lose, or draw on the rock, paper, scissors game, I think. Yep, win, lose, or draw. So how do we do that? So how do we get the result back from the rock, paper, scissors game? So I'm going to do it in a way that I think you'll understand best. This rock, paper, scissors game, though, basically needs to return, let's say, a string that can be used to check the status of the game. So let's just do one example. So let's say in a rock, paper, scissors game. So if the player play is a rock and the computer play is a rock, then we will return draw. And then we can say else if the player play is a rock and the computer play is, what's number 2? That's paper. Then that's a loss, right? Because the computer covered our rock with paper. Else if player play is a rock and the computer play is a scissor, that is a win because our rock crushes their scissor. Many more else ifs if follow. That's just what happens in the possible combinations of me playing a rock. I could draw if the computer plays a rock. I could lose if the computer plays paper, and I could win if the computer plays scissors. Hopefully you remember from last week that I made that decision last week that number 1 means rock, number 2 means paper, number 3 means scissors. We have not handled the code to ask the player what they want to play. That is work that you will do. But anyway, now we actually have the function returning draw, loss, win, and we can use that. So down here in this part of the program, we can say result. We will get a result from the rock, paper, scissors function, and then we can say if the result is a win, then we will bump up P wins by 1. Else if the result is a loss, then we will bump up RSP losses by 1. Else if the result is a draw, there's not anything else it could be, but let's go ahead and be explicit. Then we will bump up the draws by 1. So there's an example of how to do the counters. And then at the end of the program, and by the end I mean after the for loop, but before the program closes, I'm checking the curly braces, we can spit out to follow. So Kevin K asked, could I make this its own function? Yeah, I could make this whole counter thing its own function, although it would actually be a lot harder to keep track of the counters while the person's playing for possibly a long time. So I could do it in a function, but it's actually harder to do the counters part with a function. It's easier to do the counters part just right here alongside the menu. So that's what I would recommend. Even though I could do it, it would be harder to code in a separate function because the variables would be hard to manage over time. So for the counters, by far the easiest way to manage it is just to have the counters here, count them up here, and then print out the results here as well, which is going to make for a nasty bit of code, but it is by far the easiest way to do it. Okay, so good question though. So there's some starter stuff. As I'm shutting down here, I will leave this stuff on my live stream screen for you to look at more carefully. So let us make the final function, which is number guesser. We know that it's going to return win or lose. We also know I can't remember what's the number supposed to be between 1 and 100. So we already know how to do this stuff. 1 and 100. So for my money, I'm going to use a condition loop for this. So the condition loop, the reason I'm using that is because there's two conditions. One condition is that they correctly guess the number. The other condition is that they have run out of guesses. So let's set up for that. We're going to have there's the computer number. We will have the player guess, which will be an integer, which will be a 0 value variable, which is fine. And then we will have a the number of guesses used. And we know they're going to guess at least once, so we will start the guesses used at 1. So there's all our variables. We have the random number between 1 and 100. We have the player guess, which we are about to ask them for, but not yet. And then we have how many guesses have they used, and then we'll set up a loop. So 4, the guesses used is less than or equal to, actually less than 5, right? You only get 5. Yep. So you only get 5 guesses, and you haven't guessed the right number. So 2 conditions. You have a limit on your number of guesses, and also there's no point in asking you to guess if you actually have guessed the number that matches the random one. Let me call it random number. So I'm using a condition loop. First thing I'm going to do is make sure that I do the adjustment part, which I will do at the end of the loop. So now we're in the guessing game. So what do? Prompt for the player's guess. Scan the player's guess. So there's the number guesser loop. Get a random number. This is going to be 0 to start. That's fine. And we'll give them a limited number of guesses. We will stop at 5. 5 is harsh, by the way. I probably said you can adjust that. Yeah, you can adjust that from 5 to other stuff. 5 is pretty unfair. Okay, so now I have a loop that will go on until they have used up all their guesses or they happen to get the right number. So then after the loop, so this is what's tricky about the number guesser is that we have to wait until after the loop to know what the result was. So basically, after the loop, if the player has guessed correctly, so if we find ourselves at the end of the guessing repetition because the player found the right number, then they won. The only other way that we would be here is because they lost, which is why the string is here. So that's most of the number guesser. I took away most of the fun there. So I need to stop. It's almost 5:50, so I've gone on well into your late afternoons, if not evenings. So thanks a bunch for being here. And if you would manage to stick around this long, then thank you for your patience. It's going to be a lot of video to watch, I know, but I'm sharing with you the code samples and the starter solution for the lab. I am not directly sharing the project, but I am going to stop here for the next few minutes and show you screenfuls of the partial solutions that I am given. So here's the top of the program. And the imports I'm using, which is FUMP for printing and scanning, random numbers, seeding random numbers, and that's all we should need. Okay, so I'll stop, just count off a little bit, loop. All right, the number guesser part. Let me push rock, paper, scissors out of the way. So there's the number guesser code. It's not complete, but it has a lot of what you don't have to do it this way, by the way. But if you are feeling a little bit lost about where to go with it, here is a starter, which still requires that you do some work to complete it. I will point out to you while this screen is up that this 5 is a very tough number of guesses. You'd have to get lucky. So you might play around with that number 5 and make the game a little bit more fair for the user. So this function returns when they guess right, loss otherwise. That's the number guesser game. So now let's look at rock, paper, scissors. Can I get it all on the screen? Can I move this? Or no. Can I do it like, okay, yeah. Yes, it all fits. It's not complete. It also returns a string, win, lose, win, loss, or draw. So the way this function works is we need the computer to make their random selection. I picked 1, 2, and 3. Rock, scissor. Oh, I did rock, paper, scissor. 1 is rock, 2 is paper, 3 is scissor. So when I prompt the user for their input, that needs to match, right? So I need to tell the user, type 1 for rock, enter 2 for paper, enter 3 for scissor. Now I can show them what the computer played. So now that I know what they played, I can tell them, hey, the computer played rock. You might also do a I would recommend it at least that you print a computer plays rock, you play paper. Just to confirm for the user and for yourself when you're testing your code that you have matched the right numbers to the right play. Okay, and then the last thing in this function is a big ol' Horkin big decision tree that will have, there are other ways to do it, but you could think of this as a 9-branch tree because there are 9, is it 9? Yeah, right, 9 combinations to check. This is the player plays rock combinations with all the computer plays. You'll need the player plays paper combinations with all the possible computer plays. And then you will also need a player plays scissors with all the possible. That's 9 branches, each of them having their different win, loss, or draw. And then, so that's rock, paper, scissors. And finally, main. Seed the random number generator because both of the games use it. I set up some counters because the requirement on the project is that I keep count of their wins and losses in the number guesser and win, losses, and draws from the rock, paper, scissors game. Okay, now I enter a loop. Why a loop here? Because we want this game, this program with the different game options to keep playing over and over. So they'll play a game and then the menu will repeat. They'll play a different game, the menu repeats. And this whole menu sequence will continue until they say, I don't want to play anymore. Option 3. Okay, so we get their choice off the menu. Now we can say result equals number guesser. And then a decision tree to adjust the appropriate number guesser counters. Um, here's the rock, paper, scissors and its decision tree to properly adjust the counters. And then the break statement, which breaks the nearest loop, which is ends here on line 99. I know that because if I click next to that curly brace on line 99 and scroll up, I will see that on line 70, that is the other end of the for loop. So this part is everything after they said, I want to quit now, which is where we tell them, here's all of your wins, losses, and draws for rock, scissors, paper, and your wins and losses for number guesser. Okay, that's a lot. I hope that helps. You don't have to do it in any way like I did it. If you have other ideas that still achieve the goals of the project, then do that. Please look at the scoring rubric on the project, just like you would on a lab, carefully. 25 points for documentation, 25 points for nice formatting throughout in your code. 50 points that what I see on the screen when I'm playing with your program looks nice. 100 points for all those counters that we added in today, partially. 150 points that the number guesser game works correctly, and 150 points that the rock, paper, scissors game works correctly. You can add additional functions as you see fit. So there's no limit on the functions if you want to add more or break apart some of the games into their functions. That's up to you. And then you can see the program flow in my sample output. And then a little thing with the counters at the end. So yeah, that's it. I need to stop, don't I? Wow. Thanks a lot for your patience. Hopefully we will be more efficient in future weeks, but we do have a project coming up on Sunday, and I didn't want to leave you hanging on anything that's big about the project. So best of luck this week. I hope you have a great week. Thanks for those of you who could be here live and had the courage to chat and venture answers to questions. That's not an easy thing to do. It takes some courage, especially when you are seeing some concept for the first time. So much respect to you guys for doing that, for being here and venturing those answers. And Canvas Inbox, Piazza, office hours. If you have questions as you work through the lab this week, which I've given you most of the solution, and I will share links to that on the lecture page. And best of luck on the project, which now I hope that you've seen the live stream and you're here to the end of the video. You'll see that I've given you a lot of the building blocks for it. Okay. Have a good week. I will see you on Tuesday next week. My voice is beat.